across the globe.
Wow, now we're booking.
To some surprising places.
I'm a high-tech redneck.
I want to see if any of this incredible science
Doesn't look a lot like a gun.
is going to help us save the planet.
Ladies and gentlemen, boys and girls of the world, meet your savior.
I'm Sean Riley. I've seen some pretty big fixes in my time, but this is the biggest. My first stop is New York City. Everyone knows that greenhouse gases are piling up, and the Earth is getting hotter and hotter. This cab ride alone will put almost 7 pounds of CO2 in the air. We're all adding to the problem, one molecule at a time, block by block, across the globe. What I bet you didn't know is that scientists are developing some far-out fixes. So controversial that even the UN is trying to ban them. But if push came to shove, could one of these ideas really save the planet? I'm gonna find out. First up, a couple of guys at Columbia University who have figured out how to scrub the skies clean of carbon. Physicists Klaus Lochner and Alan Wright are working with an incredible material that can pull CO2 out of the thin air.
This is our air capture media.
This is it. This is the material I came to see.
That's the stuff, yeah.
Now I know what you're thinking. Mother Nature has already invented a machine to do that for us. It's called a tree. But trees are fighting a losing battle. We're producing gigatons more carbon than all the vegetation on Earth can handle. Klaus and Alan think they have solved that problem. They've discovered this material is a more effective CO2 capture device than any tree.
I was just curious, so I took one of these and stuffed it in a Ziploc bag and added a bunch of water and squished it out and then sealed it, and the Ziploc bag inflated.
For some reason, this brush was giving off CO2, and lots of it. But the most astounding thing was when it dried, it sucked CO2 back out of the air. Carbon capture and release at will. They're still trying to figure out why it works, but the fact is, it works.
So how do you actually turn this into this?
Well, we're resourceful if nothing else. So what we use is a highly technical instrument we call a pasta maker.
Instant carbon absorbing, high surface area pasta.
There you go.
I'm skeptical, but Klaus and Alan let their magic brushes speak for themselves.
This is the airtight chamber, and you can see up here on the panel, currently there are 475 parts per million of CO2. So it's a little higher than outside, but that's because we're in the room and the door to this chamber is open right now.
What's a normal CO2 level for outside?
390 parts per million is where the world is right now. At the beginning of the Industrial Revolution, we were at 280.
Carbon dioxide in the atmosphere traps heat from the sun. The higher the parts per million, the hotter the Earth gets. Most scientists think that major climate change is right around the corner, at 450 parts per million.
So this material is now actively absorbing CO2 out of the air inside the box?
Yes, and if you watch the red line, you can actually already see that it's now moving downward because these two brushes are absorbing the CO2 that is in there.
That's amazing. We're less than 2 minutes into it, and I can already see it's starting to lower the amount of CO2 inside the box.
And that's what they're supposed to do.
The potential of this discovery is huge. We could stop the clock on global warming and bring the environment back in time. We're now back to the year 2005 and speeding towards the dawn of the industrial age.
In about 5 minutes, you've gone down 100 parts per million.
Which means we collected a little shot glass full of pure CO2 out of that air inside.
Right.
After an hour, the CO2 level in the chamber has dropped to 275 parts per million, about where we were in the Middle Ages. But can this little brush have an impact out there in the real world? Klaus and Alan think so. They see their material as the key to building a full-scale machine, with a cylinder of absorbers and a processing unit. These machines could be planted by the thousands in remote, dry areas of the world, each one capturing the same carbon in one day as a tree does in a lifetime. So, would a world full of synthetic super trees do the trick? Okay, it's time for a reality check. We know Klaus and Allen's CO2 capture technology works.
That's carbon dioxide.
The machine would be simple, requiring only water and a little bit of energy to operate. But there's still a lot of research and development to do. And it would take 60 million of these to offset our emissions.
That's a few big car plants in the world would do that. Right? So it seems to me the scale is well within the scope of what we know how to do industrially.
Right. Once you've managed to capture it with your technology, what do you do with the CO2?
Burning coal accounts for about 20% of all greenhouse gases in the world. But it's how we stay plugged in and powered up. At the Mountaineer Power Plant in West Virginia, Charlie Powell's job is straightforward. Keep the electricity flowing.
Most people don't know what's behind the light switch on the wall. All they know is whether it works or not.
Right. Ladies and gentlemen, that's what's behind the light switch on the wall.
He's back there, burning coal day in and day out, pumping millions of tons of CO2 into the sky each year.
Now this is all after the power produced.
At the other end of the plant, engineer Gary Spitznagel is trying to figure out what to do with all that CO2.
So all this infrastructure we're walking through right now was all added on to the power plant just for the purposes of capturing carbon.
Everything you see here is specifically for this project.
Wow.
Gary tells me that this 5-story high maze of pipes and tanks captures nearly 100,000 tons of CO2 a year. That's roughly the equivalent of 275 of Klaus and Allen's synthetic trees.
Sorry, multiple truckloads each day.
You've got a way to get it out. Now you've got this huge volume of CO2 on your hands. What do you do with it?
Where it makes a 90-degree turn.
It turns out the answer is right below our feet.
So we're taking 275 tons a day of CO2 that we'd normally be venting into the atmosphere. We're pumping it 8,000 feet below the ground.
They've run pipelines over 1.5 miles below the power plant into 2 separate layers of porous rock. Compressed CO2 is pumped down and actually injected into these geologic formations, where it is trapped below an impermeable zone of dense rock. It seems logical. We pulled the carbon out of the ground. Now we're going to put it back. So, what's the reality? Studies show we could store significant amounts of CO2 underground. But there are only certain regions of the world where the perfect geology for sequestration exists. A lot of power plants will still be emitting greenhouse gases. And just like in the oil industry, there's always the danger of a leak. Not to mention, we'd have to roll up our sleeves and get to work.
No matter what the technology is, whether it's Lochner's or yours, we're talking serious infrastructure.
When I look at the big picture, you can't see anything short of a moonshot type effort. Something that truly takes the efforts of an enormous group of people trying to solve the problem from a lot of different angles, putting huge effort into it.
What would be simpler, cheaper, something we could do across the globe? Some scientists think the answer is lying at the bottom of the ocean. Next stop, the North Atlantic. The tiny island of Bermuda is over 600 miles from the nearest dry land, which makes it the perfect launching point for this leg of my search. This morning, I'm headed out to sea to check out a remarkably simple way to reduce global CO2 levels.
Welcome aboard. Thank you.
It turns out the key to this big fix might be one of the smallest creatures on Earth, plankton. Tiny plants gulping huge amounts of carbon dioxide out of the sky. Dr. Michael Lomas works at the Bermuda Institute of Ocean Sciences.
This is your toy.
Yeah, this is it.
He's trying to understand how the chemistry of the ocean works.
Something's driving the entire system to a much higher CO2.
I got news for you. The something's you and me.
Could be.
We're dumping tons of CO2 into the atmosphere. And phytoplankton is sucking about 1/3 of it up. Just like plants on land, these huge patches of algae need CO2 to live. And they dwarf any forest. Algae can be found on almost 70% of the Earth's surface. A simple organism that can capture carbon just like Klaus and Allen's synthetic tree and lock it away forever like Gary's CO2 pipeline. And the best part is, it's happening right now.
So this is the real-time readout of that CTD sensor that's in the water. The green line is actually a proxy for phytoplankton biomass. And you can see that there's actually a spike here, somewhere around 60 meters.
CO2 is pulled out of the air by plankton living just below the surface. When they die, they sink to the bottom, taking the captured carbon with them, where it will remain for thousands of years. It's a massive carbon pipeline to the bottom of the ocean.
So we're going to actually deploy now our plankton net so we can actually catch some of those animals.
But can we make this plankton work harder for us?
So there it goes, it's in the water.
Well, if we know that the phytoplankton and plants are down there doing their job, is there a way to actually manually go in there and tweak their population, increase the amount of plants in the ocean?
Well, there's a number of things we can potentially try.
In some regions of the ocean, algae need iron to grow and multiply. One idea? Feed them. In 2002, this group set out for the coast of Antarctica to see if they could supercharge algae growth by adding iron. They spread tons of iron dust across almost 20 square miles of barren ocean. The fertilization experiment was a success. Within a few days, the sea turned green with plant life.
Each net has a different mesh size. This one's a 200 micron. So that's, twice the thickness of a human hair.
And you're telling me that these little organisms right here in this jar could help save the world?
Absolutely. This sort of greenish-brown layer that's floating to the top in this sample, those are all the single-cell plants in the ocean that conduct photosynthesis every day, and potentially, if they were to sink to the deep ocean, would remove that carbon and take that carbon right out of the atmosphere.
It's the simplest idea I've heard yet.
Ladies and gentlemen, boys and girls of the world, meet your savior.
But this isn't like fertilizing your front lawn. We're talking about millions of square miles of ocean. Sequestering gigatons more carbon with microscopic plants isn't going to be easy. We'd need a fleet of ships crisscrossing the planet, systematically spreading iron over vast areas of ocean. The goal is to produce carbon-hungry algae blooms thousands of miles wide. Hold on a second here. This is starting to sound like a giant biochemistry experiment gone amok. Is ocean iron fertilization really the way to reduce global warming? Let's look at the pros and cons. We've proven we can grow more phytoplankton, and we know we can do it relatively cheaply with iron. But this is risky business. Dead algae may sink carbon to the bottom of the ocean, but it can also starve marine life of oxygen. And there's no way to know how much carbon is actually being sequestered. So, is it worth taking the chance? Dr. Lomas doesn't think so.
We don't understand how all of those things interconnect to give us the ecosystem we observe at any point in time.
Right.
There's a lot going on and a lot of interactions that we think we understand, but clearly don't understand as well as we need to.
Ocean iron fertilization may seem like a simpler way to cool the Earth. But letting the genie out of this bottle might be a big mistake. Meanwhile, almost 800 miles to the north, the clock is still ticking. The waters around Manhattan have risen about 15 inches since the start of the Industrial Revolution. New York City is already dealing with the threat of rising sea levels. But outside the city limits, people are finding solutions that are a little more down to earth. Nestled in the mountains of West Virginia, there's a man who's sequestering carbon before it ever leaves the ground.
Hey, Sean Riley.
Hey, how you doing?
How you doing? What brings you to the farm?
I came to see you. Get out of here.
Josh Fry is a chicken farmer.
Chickens is my life. Sean, here's some plastic boots for...
Now, when you think of greenhouse gases, power production and automobiles come to mind as the two main offenders. But I bet you didn't know chickens are right up there too.
That is a lot of chickens.
That's 30,000 chickens that you're looking at.
Okay, not just chickens. Livestock constitutes nearly 20% of all global emissions. Josh has found a way to keep his carbon out of the atmosphere. But I'm warning you, it's messy business.
What do these chickens do mostly all day?
They eat and poop all day long. That's it.
It all adds up to a funky-smelling situation. Josh has figured out how to transform this mess from a problem into a solution.
This is my contraption. This is a fixed bed gasifier where I cook the poop into carbon.
Cook poop? What is this guy talking about?
It really is a simple process.
Here's how it works. A chicken poops on a chicken farm. As soon as it hits the ground, it begins to decompose and release greenhouse gases into the atmosphere. But if you take that manure and cook it slowly in a gasifier, you get two things: hot gas and a charcoal called biochar. This biochar locks carbon away, keeping it out of the atmosphere for hundreds, maybe thousands of years.
Are we fired up?
Fired up.
All right, let's go. So this is the brain.
This is the brain.
Okay, starting up.
For Josh, burning manure means free heat.
Look at all this. This is not what you would normally find in a chicken farm.
Not normally, no. I'm a high-tech redneck. Yeah.
But it's the biochar Josh is making that could help cool the planet.
All right, Josh, here it comes.
And it might just make Josh Fry a richer man in the process.
Stuff, huh?
This is biochar. Black gold, the new black gold.
It turns out all that fixed carbon works as a super fertilizer, too. Josh is currently coming up with a business plan to sell his 9,000-pound-a-day yield. Look for Fryochar soon at your local garden center or home improvement store.
You think maybe that could save the world?
It will help save the world, yes, in conjunction with other things.
Biochar shows a lot of promise, but it could take a long time to go global with this technology, and it would be costly. Josh's rig came with a price tag of about $1 million. And we can't reduce emissions from power plants or cars with biochar. I still haven't found the silver bullet to fix the Earth. Next stop, San Francisco. There's an atmospheric scientist on the West Coast who has a completely mind-blowing new way to cool the planet. Total carbon dioxide emitted to get me there: over 10 tons. Hopefully, this will be the answer to all of our problems.
It's certainly good to deploy all this new technology, but it's not going to be enough.
Ken Caldera has been studying climate change for almost 25 years.
Somewhere in the world, a coal-fired power plant is being built at a rate of at least one a week.
So there's more to come.
He's got a pretty major news bulletin for me. It may be too late to save the planet by reducing CO2, but there is hope.
We don't have a better way of cooling the planet, but we do have a different way of cooling the planet, a way that's completely different from greenhouse gas emissions reduction, a way that can cool the planet very quickly.
Okay, so how is this different?
Let's imagine that this garden here is our world. The gases in the atmosphere create the greenhouse effect that we've all heard about.
Okay, that paints a picture.
The problem is that we've been putting more greenhouse gases in the atmosphere, and that's a little bit like closing the windows on the greenhouse and keeping that energy in, making the greenhouse hotter.
So what's the alternative?
If we think of a car parked in the sun, which is more or less the same thing as a greenhouse, one thing that we could do quickly is to put one of these shiny reflective things in the window, and that will reflect sunlight away from the car and cool the interior right away. And we can do the same thing with our planet.
So you're saying there's a way for us to reflect some of the sunlight before it even makes it into the greenhouse?
That's right, exactly.
Wow. Blocking the sun to keep the planet from heating up in the first place. This is a game changer. Everything I've seen so far has focused on the challenge of dealing with CO2. But there are scientists out there working on ways to reflect heat away from the planet. Shades for the whole world. One idea I've heard about is straight out of the pages of a science fiction novel. Create a massive array of mirrors in space. 16 trillion reflective disks almost 1 million miles from Earth, working in tandem to shade the planet. But this is pushing the boundaries of what humans are even capable of. It makes putting a man on the moon look like a cakewalk. To haul an estimated 20 million tons of disks into space would require over 700,000 space shuttle flights, and the price tag would be mind-boggling. We're talking an obscene amount of money. Okay, I'm due back on planet Earth now. The Rocky Mountains, to be specific. I've landed in the old mining town of Gold Hill, Colorado.
Hello. Oh, hi. Hi, I'm Sean Riley.
Physicist John Latham lives a semi-retired life in a cabin perched on the mountainside here. He doesn't think we need mirrors in space. We've already got them right here on Earth. They're called clouds. Decades of research have led him to a pretty stunning conclusion. We can engineer them to reflect more heat away from the planet.
Is this something that happens already with the clouds that we have?
Yes, all clouds reflect sunlight back into space, some much more than others.
Think about it. When a cloud passes over you on a warm, sunny day, ever notice a chill in the air? That's because water droplets in the cloud act like tiny mirrors, reflecting enormous amounts of solar energy back into space. Dr. Latham's idea: add more mirrors. It turns out, if you seed clouds with tiny particles of salt, they will attract more water and create denser, more reflective clouds.
Well, they are rather like the ones over there.
We know we can make rain by seeding clouds. The challenge here is to create microscopic drops that will simply make the clouds denser and wider, and to figure out how to spray billions upon billions of them into the sky. There's only one place on Earth where I might find a system like that. Next up, Silicon Valley. Microsprayers creating shinier clouds? I'm skeptical, but there's no way I'm gonna miss this.
I figure the guys in here are busy saving the world. The least I can do is bring donuts.
This looks good.
Dr. Armand Nukerman and his team are trying to create the perfect drop of salt water. They've dubbed it Project Silver Lining. And today, they're putting their latest theory to the test. These guys are closing in on success.
How small are you trying to get?
We're trying to get about 100 times smaller than what we have here.
Right, you're getting out bowling balls, and you really need marbles.
Yeah.
So how small do these drops have to be in order to go up? The average grain of table salt is about 1/3 of a millimeter wide. They have created droplets this size, but they need to be this small to make it up into the clouds.
And now, let's check to make sure everything's ready. We got the air, the purge air on the analyzer.
Okay.
Temperature is
376.
Dr. Nukerman thinks superheating the salt water may produce tiny drops that will rise skyward.
But 376, is that hot enough?
That's hot enough. We have our bleed air on. Software here is ready to go, and we'll start collecting data and go.
So what you're seeing now, I cut off the flow, the liquid that's coming in, and there's no sputtering through.
Immediately, even without seeing the numbers, it's just a completely different output with the heat. You can see it rising up in tiny particles.
Yeah. This won't stop.
Yeah.
Today's test was the result of 2 years of work.
Right. Was that a success?
Well, moderate success, yeah.
Yeah.
Salt particles captured on this wafer are the proof. Spraying billions of these into the sky may prevent the planet from heating up. And it's the first technology I've seen that could be deployed regionally in emergency situations where things are boiling over right now. Places like the Greenland ice shelf. This 650,000 square mile chunk of ice is disappearing at a rate of about 60 cubic miles per year. Long-term melting could cause global sea levels to rise over 20 feet, flooding many of the world's major cities. Cloud whitening may be a way to keep this place cool while we begin to get the global CO2 problem under control. So, it's off to Greenland to build sprayer machines, right? Not so fast. John Latham thinks the most efficient plan is to brighten clouds at sea and let natural weather patterns take them to their final destination. His futuristic vision? An armada of saltwater spraying catamarans. These boats would crisscross the globe, creating whiter, more reflective clouds wherever they're needed. To keep them carbon neutral, these ships would need to be powered by only the wind and sun, and they've got to be unmanned. But robotic sailboats seem a bit unrealistic. So what's the answer? Latham thinks we need to look back in history. In 1925, a young German engineer named Anton Flettner unveiled a new type of sailing ship to the world. He claimed his rotor ship was powered by blue coal, his name for wind energy. But interest in the Flettner rotor quickly faded in favor of cheap fossil fuels. Is this lost technology the way to power Latham's cloud whitening ship? Pack your bags. Next stop, Germany. Just south of the border with Denmark is the port of Flensburg. It's a small town with shipbuilding in its blood. I've come halfway around the world to visit two guys who have built an amazing sailboat.
It's kind of hard to believe, looking at it, that you could power a boat using just this cylinder.
Nun, also der Zylinder muss sich drehen, sonst geht es nicht.
Lutz Fieser and Renee Stockowitz's sailboat is called the Unicat. Solar-powered batteries spin the rotor, and the wind hitting the rotor makes the boat go. No sails, no ropes, no pulleys. It works because of the Magnus effect.
Okay, let's go.
When wind hits the spinning rotor, it creates high pressure on the side spinning into the wind, and low pressure on the side spinning with the wind. This low pressure area creates suction, pulling the boat towards it. That translates into a wild ride across the Baltic Sea.
Good. Wow, now we're booking.
The faster we spin the rotor, the faster the boat goes.
Lutz, I have to say, it works. Works well. It's hard to believe that this small spinning cylinder could power us like this.
But can we build a fleet of ships to sail around the world on autopilot?
Ich habe meine Bedenken, dass es funktioniert. Wir haben beim Andrehen des Rotors ein Gegendrehmoment und dieses Gegendrehmoment dreht das Schiff in den Wind. Und wenn das Schiff in die Situation gekommen ist, kann man es nur mit einigen Tricks wieder zum Segel bringen.
Even if a Flettner rotor ship could be piloted robotically, there's no substitute for a skipper who knows his craft. Going from this to this may still be on the distant horizon. Case in point, on the trip back, our solar batteries run out of juice, and we have to take matters into our own hands.
Okay, so maybe, just maybe, the Flettner rotor isn't the answer.
Das wird aber nicht mit aufgenommen. Gezeigt.
Unless you're gonna get giant teams of robots with paddles.
Despite the power outage, I think this plan could theoretically work. The technology is within our reach. a robotic Flettner-powered vessel might work with more development. And the spray system Dr. Newkerman is perfecting looks promising. But taking this to the next level is controversial. Studies show that cloud whitening might alter weather patterns and ocean currents. On the positive side, if the sprayers were shut off, the effects would disappear within a few weeks. But international organizations like the UN aren't sure it's worth the risk. They've called for a ban on large-scale experiments. But there's another way to deflect heat away from the surface of the Earth. An approach so controversial, it makes tinkering with clouds look like child's play. June 1991, the Philippine Islands. Mount Pinatubo erupts, spewing about 20 million tons of sulfur dioxide into the stratosphere. Over the next year, the temperature of the planet dropped almost 1 degree Fahrenheit.
And so after Mount Pinatubo, all these little particles in the stratosphere reflected around 2% of the incoming sunlight back to space.
It got atmospheric scientists like Ken Caldera wondering, could we do this intentionally? Is it possible to create a dimmer switch for the planet?
Is this really practical? I mean, can we really do this?
We know it will basically work. We don't know all the details of what would happen if we did it.
Some of the possible side effects of this controversial approach are shocking. Acid rain, drought, destruction of the ozone layer.
There's always going to be an element of risk because we only have one planet and we never really get to test this at full scale.
You don't test the parachute until you have to jump.
You know, if the plane's going to crash, but you're better off with that parachute than without that parachute.
This parachute has some pretty nasty strings attached to it. But if the climate starts changing dramatically, we may have to pull the ripcord, which is why a number of people are working on the most challenging part of this plan, delivering 1 million tons of sulfur about 20 miles into the sky. I managed to schedule a meeting in between flights with the only guy in the world who has analyzed every option.
That sounds good. When someone tells you they want to put 1 million metric tons or 1 million tons of something up into the atmosphere, that's sort of a difficult number to really visualize.
Aerospace engineer Justin McClellan has spent the better part of a year trying to figure it out.
So the goal of the study was first to determine the feasibility.
So not saying will it work, but saying can this be done?
Can it even be done? I mean, and then attaching a price to that.
The first thing McClellan and his team looked at was a really big gun. The idea is simple. Point a large caliber naval gun with SO2 filled projectiles into the sky and pull the trigger. As the projectile hits the target altitude of 100,000 feet, eject the payload before the shell falls back to Earth. The problem is, it would take 14 million shots a year. Hundreds of guns firing every few seconds, day in and day out. The gunpowder alone would cost almost $100 billion per year. But there's a futuristic gun that could deliver sulfur dioxide to the stratosphere for less. Our crew has been allowed a rare glimpse inside the Naval Surface Warfare Center in Dahlgren, Virginia, to see a brand new long-range weapon called the electromagnetic railgun. You can forget about the price of gunpowder. This gun uses electricity.
It strips away when the
Rear Admiral Nevin Carr thinks it's going to revolutionize naval warfare.
We can throw a projectile out of a gun like this about 200 nautical miles. It's much farther than any gun can shoot today in the U.S. Navy.
But you don't just plug the railgun into a wall socket. First, a bank of capacitors is charged up with 11,000 volts of electricity. To fire the gun, all that stored energy is dumped at once, like a camera flash. This massive pulse of power generates an electromagnetic field in the gun, accelerating the projectile from 0 to Mach 7 in the blink of an eye. For today's test, the team will fire an 11-pound projectile. Once it's loaded, we go to high alert. This warehouse is about to become a supercharged electric powder keg.
All right, 2 barrels. Video. Ready. Range instrumentation.
Ready. Now, as we stand right now, everybody's been cleared out of the other room where the railgun is.
That's right. There's no personnel behind the fence right now.
Team member Vanessa Lent talks me through the firing
All
sequence.
stations going to high power.
Time to see what this thing can do.
High voltage is on. 4 kV.
4,000 volts are going to go to 11,000 volts.
Right.
The capacitors slowly draw energy from the power grid. It makes me wonder, how much coal is being burned back in West Virginia to charge this thing?
7 kV.
The Navy thinks this is the future of naval warfare.
Enabling.
But could it launch enough sulfur into the sky to guarantee the future of the planet?
3, 2, 1, fire.
The sound of 11,000 volts of electricity is deafening. The projectile explodes out of the barrel at over 5,000 miles per hour. It's mind-bending, futuristic stuff. The railgun could easily deliver sulfur to the stratosphere, but the Navy won't be firing payloads much bigger than about 66 pounds. So we need to launch a lot of rounds into the sky to save the world. Almost 1 million sulfur missiles each and every day. Blasting sulfur into the sky doesn't look like it's going to be feasible. Time for another meeting with Justin McClellan.
Yeah, the guns really start to look not so good the more you look into it.
It turns out he's done the research and he's got the answer. My quest to save the planet has been all over the map. From looking at ways to pull greenhouse gas from the air, to cooling the planet by deflecting the sun's rays. And now Justin tells me he has the answer.
So I've got a pretty good idea at this point about what doesn't work. But what does work?
Well, the answer is actually right outside the window. It's airplanes.
After 8 months of gathering information and crunching numbers, Justin's final assessment makes sense.
There's an infrastructure for it. There's experience using it and operating them. So it's really the answer.
The challenge would be to engineer these birds to reach 100,000 feet.
A typical commercial airliner might fly at about 35,000 feet, and then by the end of the trip might be up at about 40. A business jet might do about 40 to 50,000 feet.
Think private business jet on steroids. The entire operation would run out of 3 existing airports located near the equator. Small, fast cargo jets, rigged to carry SO2, could deliver load after load.
All in all, this is not sounding like a huge operation.
Yeah, it's a pretty small operation, especially when you compare it to some of the bigger airlines. There's probably millions of tons in the air right now on airplanes around the world.
So there it is, a way to cool the planet right now. But if there's anything I've learned on this quest, it's that everything has a price. If we reach the point where we need this to save the Earth, we'd better be prepared to deal with some tough choices. Do we save the ice shelf in Greenland, only to cause droughts in Asia and Africa? Do we settle for a future of bleached out skies and sulfuric acid sunsets to save New York City or Mumbai from being flooded? By deploying sulfur, we could start to see a cooler Earth within weeks. It's tempting.
Even if we managed to get a system up and running that delivered SO2 and successfully lowered the temperature of the planet, you've still just sort of artificially lowered the temperature. If you ever stop doing that, it goes right back up.
Yeah, you've just put a Band-Aid on the problem.
No matter how controversial this approach is, some scientists think we'd better know how to use it, just in case. But for all these high-tech solutions and pie-in-the-sky emergency parachutes, there's no escaping that we need to stay grounded and get to the root of the problem.
Morning, sir. How you doing? I'm Sean Riley.
Sean? Dan Jackson.
Whether it's installing white rooftops to deflect heat away from cities and save energy.
This is technology that we know has a track record of working.
Or shading our planet one window at a time.
There's so many things that anyone could do in